Welcome back, everyone. So the last time we were at this point where we defined differentiability, and assuming a function was differentiable, we calculated the derivative matrix in a couple of examples. So let's continue from this point onwards. If f is differentiable at A, then it is continuous at A. Okay, this is a basic property we would expect. If this property were not true, then the fault lies with our definition of differentiability rather than the theorem itself. Yeah? So the proof is exactly the same, more or less the same as the one variable calculus proof, just that it involves a little bit more bookkeeping. So the idea is to look at the error made in the linear approximation, so to say. Yeah? So you have a linear map, this is the error, and this is less than, this divided by h goes to 0 as long as h is small enough. So this is less than epsilon over 2 whenever h is less than delta. Yeah? Now at this point we can assume that delta is less than 1, because if it was not less than 1, simply choose some delta which is less than 1, the inequality will still be true. So by the triangle inequality, we can easily see that this difference is less than epsilon h divided by 2 plus norm of this linear map acting on h. Yeah? Now at this juncture, notice that if you take any norm, and suppose A is a matrix and B is a vector, right? This is the norm of what vector? It is sum of Aij Vj, in fact A1j Vj, A2j Vj, and so on. Yeah? Now you can then easily say that norm of AV is some constant that depends on A times the norm of V. Well, what sort of a constant would work? I mean, again, this is square root of sum of A1j Vj square plus, so what norm can we use? We can use, for example, the operator norm, yeah, for example. So nonetheless, this is A2j Vj square, etc. So we'll use the L2 norm for Rn. Now at this juncture, well, it's certainly not very difficult to see how to get this. There are a number of ways of seeing this. For example, this is less than mod of this, if this were complex numbers, A1j Vj square, which is less than norm of V square times A1j square, and so on, right? So in other words, this entire thing is less than norm V times square root of something that depends on A. Okay? So as a consequence, let's go back to the previous page. Over here, we can conclude that this is less than some constant times norm h, and this entire thing is less than epsilon by 2 this is less than 1 by hypothesis, provided h itself is less than epsilon by 2c. So in other words, you want h to be simultaneously less than delta 1 and epsilon by 2c, which is easily arranged. You simply take the minimum of these numbers, and if norm h is less than these three numbers, then surely this is less than epsilon divided by 2 plus epsilon divided by 2, which is equal to epsilon, right? So this proves that differentiability implies continuity. Yeah. All right. Now let's look at some properties of differentiability. If you will. Okay. Now, prior to looking at properties, we might have to make a definition. So notice that the definition of differentiability was motivated by the tangent plane approximation. In other words, just like a curve is expected to be approximated by its tangent line, if say you take z equals f of x y, that will be, for example, a surface and it's expected to be approximated by a tangent plane, right? So what then is the definition of a tangent plane, right? So the simplest way is as follows. You simply truncate the expression for the derivative. So basically we want to say that, let's say f, small f, from let's say Rn, some subset in Rn to R, okay, is a differentiable function at an interior point. Right. So what that means is it makes precise this approximation, right? That's what differentiability does. Once again, dfah. Well, what do we know about this? We already know what this is. This is the dot product of the gradient of f of a with h, which is df dxi at a times hi. Yeah? So this is the thing that it makes precise. More precisely, the difference of these expressions divided by norm h as h goes to 0 goes to 0. So taking cue from this, we define the tangent plane to the graph of the function, that is, what is the graph of a function? The graph of a function is a map from, it's a subset rather than looking at it as a map. Let's graph of f. It's basically a subset of Rn cross R consisting of x and f of x. Right, so this is xn plus 1. So we don't want to write it as h, yeah, because what we really want is to write it using x's instead of h. Yeah, so but what is x in terms of x? H, this is x. Yeah, so this is so this is the definition of a graph of a function. I mean, this is the definition of the tangent plane to the graph of a function. Once again, Okay. Right. So we'll come back to the tangent plane a little later. So far, what theorems do we know that allow us to conclude that a function is differentiable? We don't know of a single example of a differentiable function yet, right? So here is an important theorem. This is a criterion, if you wish. It's a sufficient condition. By no means is it necessary. Sufficient, not necessary. Okay. If a function f from u in Rn to Rm is C1 at an interior point A, what does C1 mean? That is, the matrix df. What is df? Maybe I'll put a vector symbol just so that we are on the same page. What is df, the derivative matrix? Well, just to recall what it is, it's simply the gradient of the first component, the gradient of the second component, etc. Okay, these are all rows, and these form the rows of the matrix. So in other words, the partial derivatives of all the components exist in a neighborhood V of A, and df, when treated as a function from V in Rn to how many components are there of this matrix? When you think of a matrix, it's simply a collection of numbers. How many numbers are there? There are mn numbers. So you think of this matrix, instead of thinking of this derivative as a matrix valued function, simply think of it as a vector valued function where you arrange all the entries of the matrix as a vector as opposed to a matrix is continuous is a continuous function. Okay. Then f is differentiable at a C1, maybe I'll say near an interior point. This is the terminology we are using. So what I'm saying is simply this. If the partial derivatives exist, then the function need not be differentiable. We've already seen examples to that effect, because differentiability implies continuity, and partial derivatives existing is not good enough for continuity. Hence, differentiability is not implied merely by the existence of partial derivatives. But if partial derivatives exist and the partial derivatives themselves are continuous functions, so we are talking about the continuity of the derivative, not the function itself. So if the partial derivatives exist and they themselves are continuous functions in a neighborhood of the point under consideration, then f is differentiable, not just at A, in fact, on V. This is not the most optimal set of hypotheses for this theorem, but we don't really care, because wherever we'll end up using it, we'll have much more at our disposal than merely this. Okay. So once again, what does the theorem say? If you're C1 near a point A, then you're differentiable near that point. Near that point in the sense you're differentiable at that point and in a neighborhood. What does C1 mean again? That the partial derivatives exist of all components and the partial derivatives themselves form a continuous function. Okay. So why is this a practical criterion? Here are examples where we can apply this criterion. So suppose I take f of xy, this is sine of x cube e raised to y plus on R2. So f is a function from R2 to R and given by this expression. By one variable calculus, notice partial derivatives, the existence of partial derivatives is simply a one variable calculus question. The partial derivatives with respect to x and y do exist, and they can be computed using the chain rule, right? You're fixing y, so this is a constant as far as you're concerned. Polynomials are differentiable, sine is differentiable, so composition of differentiable functions is differentiable, right? So this is e raised to y 3x square plus e raised to y square, and this one is cos of this, the derivative of e raised to y is e raised to y plus x times 2y e raised to y square, right? Now these functions are continuous everywhere. Why are they continuous? They're continuous because one variable functions which are continuous are already continuous. So this is continuous, this is continuous, this is continuous. These are all continuous functions. So is this, this and this. Product of continuous functions is continuous. So this is continuous, this is continuous. Now a composition of a continuous function, cosine is continuous with a continuous function. This is also continuous because products are continuous. So composition of continuous and continuous is continuous. So this is continuous. So product of these two continuous functions is continuous. And when you add continuous functions, you get something that is continuous. So the addition of this continuous function with this one is continuous. Okay. So it's just an application of the rules we have done so far. So very quickly, f is C1 on R2 and hence differentiable. Okay. Notice this would have been a very hairy affair had we done this with first principles. Consider this function. Again, each of these components, these are both C1. By the same logic as before, on all of R3. Polynomials are C1 and hence differentiable. Okay. Lastly, rational functions. Are differentiable whenever the denominator is non-zero. Once again, differentiability is defined on an open set. The set of all points in Rn where the denominator, which is a polynomial, is non-zero, that set is an open set. Why is that an open set? What does it mean to be an open set? If the denominator is not zero at a point, then we need to find an open neighborhood around that point where the denominator continues to be non-zero. Indeed, this follows from the continuity of the denominator. Please write this proof up rigorously on your own, but nonetheless. Okay. Right. Just one caution, one cautionary point, caveat here, is that this criterion is sufficient but not necessary. Indeed, here's a counterexample. A very standard counterexample. This function is certainly differentiable at x equals 0. Yeah. But the question is whether the derivative is continuous, and I'll leave it to you as an exercise to check that it is not continuous. Well, maybe I can just, so the derivative is, it turns out, maybe I'll erase this function. Times minus 1 by x square and 0 as it turns out. So this is not continuous. This goes to 0 as x goes to 0, no problem with this. The problem is with this. This keeps oscillating. For example, if you take 1 divided by x to be equal to, so cos oscillates, right? So you need to just choose a sequence of xn so that 1 divided by xn is chosen in such a way that cos oscillates between 1 and minus 1. Okay. With this hint, you should be able to choose that sequence. So I'll leave this to you as an exercise. So the bottom line is this is not necessary, okay, even in one variable calculus. In other words, the derivative, you can be differentiable even without the derivative being continuous. Okay, so proof of the criterion. Right. So, first of all, without loss of generality, m is 1. So, what is m for us? So, I'm going to call f u and rn to rm. I can assume m is 1, that is, I can assume it's a function to r. Why? Simply choose each component of f and apply this proof for each component, and therefore you can prove the case for m larger than 1. Okay. First thing is this. Our basic strategy is induction on n. So for one variable calculus, this is trivial. We already know that C1 implies differentiable because C1 already has differentiability baked into it. Okay, so induction hypothesis. Suppose the result is true. N minus 1. Okay. Then we want it to be true for n variables, right? So suppose you take the interior point A in U and you write this part as A comma B, where this is in R, this is in Rn minus 1. Then the this function is C1 at y equals b. Why is it C1? What does it mean to be C1? The partial derivatives of g exist and they are continuous in a neighborhood of y equals b. Indeed, this is true because the partial derivatives of g are precisely the partial derivatives of f with respect to y. And by hypothesis, they exist and they are continuous. So which means with derivative, let's call it L of k, this linear map, which is the derivative of f acting on 0 comma k. So the derivative is a linear map, right? What linear map is it? So we already know what this is. This is the dg dy1 at p times k1, dg dy2 times k2, etc. But what is dg dy1? It's the same as df dy1. Likewise, dg dy2 is the same as df dy2 and so on. So basically, you're simply taking df dy1 k1, df dy2 k2 and so on, and you're forgetting about differentiating f in this direction. So in other words, it's simply the derivative of f, but with 0 in the first direction and k vector in the other directions. Yeah? Okay, so what can we do at this point? What do we want to do? We want to look at the error in the linear approximation, so to say. And divide it by this vector. And we want to show that this error can be made less than epsilon, or rather it goes to 0, to go to 0. All right, now as always, our best friend is the triangle inequality. So the first thing to note is that this, being a linear map, is a sum of two things, right? Right. Okay. Now we shall add and subtract to conclude using the triangle inequality and adding slash subtracting. What we shall add and subtract is precisely this beast here. Okay. Plus the same beast and the rest minus f of ab, and what we have omitted from this one. Okay, So I've not done anything mysterious. I've just used the triangle inequality, added and subtracted. Why am I adding and subtracting precisely these things? Because here both sets of variables are varying, but I want them to vary one at a time, holding the others fixed. Okay? Here this is fixed, this varies. Yeah? Okay, so now what can we do? So note the following, that we can say something about this term. What can we say about this? First of all, instead of dividing by something larger, we can divide by something smaller at the cost of only increasing this expression. So in other words, I can completely omit, let me use another color just to make a point. We will omit this. Okay? This will only increase this expression, as I'll do in soon. Now this was precisely the linear approximation for G, which we have assumed is C1 and hence differentiable by the induction hypothesis. In other words, as h comma k goes to 0, 0, this goes to 0. Okay? Now roughly we would hope the same for this expression as well. So for one thing, we can remove this at the cost of increasing this expression. The trouble here is this would have gone to 0 by one variable calculus, provided what happens if this was, instead of b, if it was b plus k, then by one variable calculus this would have gone to 0. So what shall we do? We shall add and subtract as usual. Okay? So we'll use our standard adding and subtracting trick. So this is less than f of a plus h comma b plus k. This is the second term. The first term we need to add and subtract, so that's why I'm writing it a little later. All right, we'll just finish writing this and we'll move on. Okay. Right. So we are out of time. So thank you for joining. We'll stop here. We are out of time. So thank you for joining. We'll continue the next time.